We live in a world of whole things. When we count complete, unbroken objects, one apple, one book, 1 meter, math feels comfortable. Whole numbers are simple, intuitive, and easy to keep track of. But life rarely comes in perfect, self-contained packages. Eventually, you have to split a pizza with a friend, measure out a partial cup of flour for a recipe, or figure out how much work you can get done in half an hour. The moment a physical object is cut, whole numbers stop being useful. You can't use a 1 or a 2 to describe a single slice of a cake. The traditional counting system simply fails to describe what's sitting on your plate. To measure the real world accurately, humanity had to invent an entirely new mathematical language, a system specifically designed to map the messy, infinite spaces that exist between 0 and 1. That solution is hidden in the name itself. The English word fraction comes from the Latin word fractio, which is derived from the verb frangere, meaning quite literally, to break. Early mathematicians needed a way to translate that physical, often destructive act of breaking an object apart into a logical, written language that anyone could read. Every fraction is a mathematical transcription of a broken object, providing the specific logic of the split in written form. Before you can write down that break, there is a strict rule you have to follow. The whole must be divided into pieces of exactly the same size. If a pizza is cut into highly chaotic, random shapes, claiming you ate 3 slices tells us nothing about the food consumed. A proper fraction demands perfect uniformity. Every single piece must carry the exact same weight and area. If you lose that law of absolute equality, the entire system collapses. Fractions only work when the playing field is perfectly level. Once we have equal pieces, we can build the actual fraction, and the best place to start is right in the middle, the cut itself. This horizontal line is the fraction bar. It acts as instructions representing mathematical division. Move below the bar and we find the denominator, which tells us exactly how many equal parts the entire object has been divided into. When we read a denominator out loud, we use ordinal numbers like third, fourth, or fifth. Above the bar sits the numerator, which specifies exactly how many of those equal broken parts we are selecting, keeping, or eating. Unlike the bottom, we read the numerator using standard cardinal numbers, 1, 2, 3, and so on. Together, writing a fraction gives you a complete operational map. The bottom tells you how many cuts to make, and the top tells you how many pieces to take. To see how the numerator and denominator interact in physical space, let's map them out visually. This rectangle has 4 equal parts, a denominator of 4. Selecting 3 blocks makes our numerator 3, representing 3/4. Slicing horizontally makes 8 pieces, with 6 shaded. The colored amount hasn't changed, so it equals 6/8. Dividing both numbers by 2 simplifies it back. Fractions that look completely different on paper can describe the exact same portion of a whole. As long as the ratio between the cuts and the selections stays constant, the value remains identical. This mechanical math functions as a highly specific descriptive language used everywhere from professional kitchens to fuel laboratories. You see it whenever you slice a quarter of a cake. This gauge illustrates it perfectly. Tracking 3/4 of a fuel tank tells you exactly how much volume you have left before you run out of gas. We rely on them to measure time when we wait a half hour for an appointment, or to measure mass when we ask a butcher for a 1/4 kilogram of meat. Every time you encounter these numbers in the wild, you are reading a strict, logical story of division and selection. Grasping this anatomy of a break provides the essential groundwork for geometry, probability, and eventually the complex logic of calculus.